So we're now going to have a family-like atmosphere for this session. And so, the first speaker, Joan Moschovakis. And the title you can also.
Thank you. Well, I met Sergei, I think, in Peroslavl-Zalewski a long time ago. He was very young. I was not so young. And
Age 9. Still very young.
The program committee consists of two people from whom I learned when I was very young, and they were very young too. Anil Narod, when I was an undergraduate at Berkeley, and he was a young instructor, full of energy, wonderful set theory course. And Melvin Fetting from his book, Intuitionistic Logic, Model Theory, and Forcing. So I'm very pleased to be here and wish Sergei a very happy 60th birthday. I'll talk about sort of a housekeeping talk having to do with the axiomatization and formalization of intuitionistic analysis. And focus on the question, what does there at most one x in x with the property p of x mean constructively? If x is the natural numbers, or the binary fan, Cantor space, or the universal spread, Baire space, or a canonical set R of real number generators, or any constructive measure space. The context is that x comes equipped with an equality relation with respect to which p of x is assumed to be extensional. Equality on n, of course, is decidable. In fact, n has a primitive recursive linear ordering satisfying the usual comparability condition. Equality on Baire space and Cantor space is defined extensionally in terms of equality on the natural numbers, and is stable, but not decidable from the constructive standpoint. Equality on R is also pi01 definable because we're taking canonical representatives of the real numbers, and stable, but not decidable. Baire space, Cantor space, and the canonical reals have sigma 01 definable linear orderings in a constructive sense. You can't always tell whether x is less than y is less than x, or if they're equal. So it's really a partial linear ordering in a sense. Not decidable and not stable unless you accept Markov's principle. So this is the context. Apartness becomes important there in this context. If you have a linear ordering in this sense, x is apart from y if and only if either x is less than y or y is less than x. For the natural numbers, apartness coincides with inequality, but generally apartness is stronger. The negation of apartness coincides with equality because the negation of sigma 01 is pi01 constructively as well as classically. So at most one x in x satisfies p could be expressed constructively either by, for every x in y, if p holds of x and p holds of y, then x is equal to y, or by, for every x in y, if x is apart from y, then not p of x or not p of y, which requires a decision. Constructively, the second condition implies the first, but the first does not imply the second in general. You could write down some other variants. You'd find that they were constructively equivalent to 1, which seems to be the most straightforward, but 2 is also interesting, and in the case that p is a negation, a stronger version, 2 prime of 2, would be if x is apart from y, then either q of x or q of y. So instead of saying not Q, you say Q, right? Which is stronger. So these are our possibilities, and which one to choose would presumably depend on one's perspective. One constructive perspective is Brouwer's intuitionist perspective. We've heard quite a bit about that. And just to go over ground that you've already been over in this meeting, very briefly, some of it is specifically having to do with analysis. Brouwer rejected the arbitrary use of the law of excluded middle, but he accepted A implies not A, and therefore accepted not A implies not A. Where not A for Brouwer means that A implies a contradiction. He accepted full induction on the natural numbers, countable and dependent choice, full monotone bar induction on the universal spread, or bare space, whose points include but are not restricted to free choice sequences, generated one choice at a time, and law-like sequences determined in advance, all the choices determined in advance, and certainly any combination of these. But so far, you know, it's not very controversial, it's just a little peculiar. And now he adds the principle of continuous choice, which entails that every total function from bare space to the natural numbers is continuous in the finite initial segment topology. And this brings up the question of consistency. Is this peculiar analysis consistent? Real numbers are represented by Cauchy sequences of rationals or by nested sequences of intervals with rational endpoints. So here's Brouwer's analysis in a nutshell. He had no problem using reductio ad absurdum to derive a negative conclusion, but his proof of an existential assertion always provided a witness, or a constructive approximation to a witness. He worked informally, but Hiding, his student, published formal systems for intuitionistic propositional and predicate logic, number theory, and parts of analysis. And some of Hiding's formalisms would be recognizable today, but his formalization of analysis would not. Kolmogorov, in 1932, gave an interpretation of intuitionistic logic in terms of problems. So this resonates with what we've heard before. An implication expresses a problem of finding a general method for reducing the problem expressed by the conclusion to the problem expressed by the hypothesis. The universal statement expresses a problem of finding a general method for solving the problem. And an existential statement expresses a problem of finding a witness. Hiding used proofs instead of problems. Artyomov and his colleagues have now perfected Hiding's version of the BHK interpretation or explication of intuitionistic predicate logic. Okay? But there is a nagging consistency question. So in order to verify the consistency of Brouwer's analysis, and also to make it more comprehensible to mere mortals, Claney and Besley published an intuitionistic formal system, which I'll call FIM after the name of the book, Foundations of Intuitionistic Mathematics, especially in relation to the theory of recursive functions, which was based on an extensional two-sorted intuitionistic number theory, which I'll call IA1 to distinguish it from the HA1, which Droelstra liked to use, with axioms for some primitive recursive functional constants and axiom schemas for countable and continuous choice, and the bar theorem. And Claney proved that FIM is consistent relative to its classically correct subsystem B, by interpreting the Brouwer-Hagen-Kolmogorov explication recursively. This was the famous Kleene functional recursive realizability interpretation. So FIM is consistent and has a recursive interpretation, which anyone can understand, a classical or constructive mathematician. And Vesely used this theory to formalize part of Brouwer's real analysis. This was back in 1965, a long time ago. 4 years later, he published a monograph with the American Mathematical Society in which he developed the theory of recursive partial functionals and function realizability and a proper subsystem, very small subsystem, of the basic classically correct part of FIM. This proper subsystem I call M. It consists of two-sorted intuitionistic arithmetic plus the axiom of unique choice. This axiom schema, Meinl gave it that name, I believe. We just called it, if for every x there's a unique y such that a of x and y, then there is an alpha such that for every x, a of x and alpha of x, and I always thought of this as a kind of function comprehension principle for intuitionistic analysis. In this case, there is a unique y such that b of y abbreviates. There is a y such that b of y, and for every y and z, if b of y and b of z, then y and z are equal. So we're expressing at most 1 by option 1 here of the 2 or 2.5 options.
That's a cool answer.
Okay. I forgot to turn off mine, too.
Wish a little bit of reference to fix it.
Okay. So there is exactly 1. So what does that mean? There is exactly 1. That means there is 1, and there is at most 1, right? And first observation is that as far as you're talking about numbers, it doesn't really matter whether you use option 1 or option 2. Option 2 prime would be a little stronger still, but and maybe peculiarly, it doesn't matter if you're talking about functions either in this case, as long as you know there is one. And the reasons are different. The reason that it doesn't matter for numbers is that intuitionistic two-sorted arithmetic proves that if there is 1 and there is at most 1, according to option 1, then in fact the property is decidable. And if the property is decidable, you can always pick the least one. And so over intuitionistic two-sorted arithmetic, it doesn't matter which of options 1 or 2 you pick. A different argument shows that it also doesn't matter which one you pick, for there is a unique alpha such that b of alpha. It's a different argument because from there is a unique alpha, b of alpha, you get, using the continuity principle, that it's impossible that b should be decidable. So, well, if there's a unique alpha such that b of alpha, then for each n, there's a unique initial segment of alpha which works, and so you put this together and you get, again, that it doesn't matter. With the caveat that if b is a negative property, where if it's net not c, where c is not stable under double negation, then option 2 prime would be stronger in this context. Option 2 prime would be looking at number 4 and replacing the not b by a c, right? Okay, this brings up another question, which my student Garifolia Vafiadu observed, and she's getting her PhD, I hope, in less than a month from now. No, a little more than a month from now. This is just an observation, okay? In fact, this observation, this first one, I think, was in my dissertation a long, long, long time ago. that unique choice for numbers also gives unique choice for countable choice for functions. But she observed that it also gives the schema which we call the characteristic function principle for decidable predicates. Every decidable predicate of numbers defines a detachable species which has a characteristic function, a pretty obvious thing. And of course it also entails the quantifier-free axiom of choice, because quantifier-free or bounded quantifier-free formulas are decidable. So you can always pick the least, which is unique. One can get classical models simply that show that CFD and the quantifier-free countable choice are relatively independent over intuitionistic two-sorted arithmetic. For the first one, it's just the primitive recursively bounded functions for the type 2 objects in your model. And for the second, it's just the recursive objects. Okay. Because classically, the characteristic function principle, of course, gives you full comprehension. So you can get these independence results with classical models. What she proved in 50 pages of difficult proof theory is that not only does the minimal theory actually break down into intuitionistic two-sorted arithmetic plus the characteristic function principle plus the quantifier-free axiom of countable choice, but also Troelstra's elementary analysis, EL, does not prove the characteristic function principle. All it gives you are general recursive functions. And CFD gives more in principle. M is actually definitionally equivalent to EL plus the characteristic function principle. And this was not easy because, for one thing, EL includes names and defining equations for all primitive recursive functions. In fact, to do it right, you would have to have a name for every primitive recursive derivation. Planey was much more, he used Occam's razor. He only used assumed finitely many primitive recursive functions plus the axiom of unique choice, and was able to get all the recursive functions that way. Okay, so this is what Planey's perspective led to. Planey's perspective on Brouwer. And then there's the question about uniqueness entailing existence. In some situations, this is really an interesting question. For example, you could strengthen unique choice by requiring the uniqueness not for the y in the hypothesis, but for the alpha, and not requiring uniqueness for the y. So suppose for every x there is a y, such as a of x and y, and if alpha and beta are both choice functions, then they have to be the same. Okay? This version is actually intermediate between countable choice and unique choice. In fact, over intuitionistic two-sorted arithmetic, I think corollary 5 says it better. Over the minimal theory, which is intuitionistic arithmetic plus unique choice, this version, AC00 double unique, is equivalent to the double negation of countable choice. And it doesn't matter, again, whether at most one statement is expressed by option 1 or option 2. So far, we don't really have a difference. Okay, another perspective that one could explore would be Bishop's constructive perspective, which I like to call cautious constructivism, because Bishop based his exercise in constructivism on a strictly positive and computational version of the BHK interpretation. He accepted countable independent choice, but he remained neutral on Brouwer's bar theorem even, which is classically acceptable, and the continuous choice principle of which of course is not. So everything Bishop does is acceptable to classical mathematicians, acceptable to intuitionistic mathematicians, and also acceptable to recursive mathematicians who would not accept the bar theorem because it fails there. Okay? Many people continued Bishop's work, particularly Bridges, Richman, and Ishihara. Recent studies of unique existence by Bishop constructivists have been interpreting at most 1, either by option 2 prime or by a stronger option 3, in order to introduce the idea of uniqueness without a priori existence. Bridges advocates expressing there is at most 1 element of X with a property P by for every X and Y in X. If X is apart from Y, then P prime of X or P prime of Y, where P prime is some strong form of negation of P, which he doesn't really specify, but in each particular instance there is some kind of strengthening of P, which of the negation of P, some effective version, constructive version of the negation of P, which entails not P, but is stronger. And with this idea, they have come up with a version of Weak-Koenig's lemma, which is actually equivalent to the Fan theorem for decidable subsets of Cantor space. However, before going into that, I want to suggest a reasonable way, perhaps, of simplifying constructive reverse analysis. Till very recently, Bishop's followers have insisted on working informally, and they've said things like, we can use constructive Zermelo-Frankel, we can use choice, if countable choice if we need it, we can use, but they don't often say exactly what they've used. So in order to get sharp results in constructive reverse mathematics, it does seem that some kind of formalization or at least axiomatization is needed. And Ishihara has begun formalizing. Bridges has been working with younger people who formalize or axiomatize at least. Bridges himself describes himself as not a logician, but an analyst. And his proofs are constructive analysis proofs, typically. But in order to get negative results in particular, it seems that one needs to at least formalize some parts of the endeavor. And of course, now with Axel and Rathjen's precise treatment of constructive and intuitionistic set theory, one could use that as a basis for formalizing all of constructive reverse mathematics. But after all, constructive analysis can be expressed simply in a 2 or at most 3-sorted language of numbers and functions. It's really pretty low down. Most results in constructive reverse analysis can be understood over intuitionistic 2-sorted arithmetic, or EL, which is essentially IA1 plus quantifier-free countable choice, or Planey's minimal theory. For the rest of this talk, I'm going to use constructively equivalent to mean precisely equivalent over M. Okay? So now, weak Koenig's lemma with uniqueness. Weak Koenig's lemma is Koenig's lemma for detachable subtrees of 2 to the n, and is constructively equivalent to this. I can say that because a detachable subtree will have a characteristic function, right? So for every a, there's an alpha and 2 to the n, such that for every x less than or equal to y, rho of alpha bar of x equals 0. So this means there are arbitrarily long finite initial segments which satisfy rho of alpha bar of x is equal to 0 all the way down, right, to the end of that finite segment. Then, in fact, there is an infinite sequence such that for every x, rho of alpha bar of x is equal to 0. This is just one way of stating. You can think of, doesn't matter what the alpha for the hypothesis is for x bigger than y. It can be 0. Okay. Adding a strong effective uniqueness hypothesis gives WKL unique. This is the one that the Bishop people have been looking at. So here the uniqueness hypothesis is if alpha is apart from beta, that is, if there is an x such that alpha of x is different from beta of x, then either there is an x such that rho of alpha bar of x is different from 0, or there is an x such that rho of beta bar of x is different from 0. Okay? And interestingly, this version turns out to be constructively equivalent to Brouwer's span theorem for decidable spans. So it's nothing new. So maybe if we use a different option, we won't get anything new. So let's use option 1 instead and see what we get. Let's call that WKL W-unique. So the uniqueness hypothesis here is that if alpha and beta are 2 infinite paths, then they're the same. Okay? And pretty obviously this one is in between weak Koenig's lemma and WKL unique constructively. But it's really in between. That is, it is something new. It's not entailed by the decidable fan theorem, and it doesn't entail weak Koenig's lemma for a decidable relation. And the proof actually works by decomposing WKL W-unique into a logical principle, which is sort of a piece of Markov's principle, not all of it, and a mathematical principle, not weak Koenig's lemma, following the example of Ishihara's decomposition of WKL inverters of WKL unique. Then one shows that WKL W-unique is not G-realizable. The fan theorem is G-realizable. WKL W-unique is realizable, but WKL is not. Okay? So that gives a neat separation using known realizability notions. Okay, so you didn't do it. Now what if instead of weak Koenig's lemma, you consider Koenig's lemma itself for an arbitrary predicate R? And still working with the binary fan. I guess I should mention that constructively restricting oneself to the binary fan it's not much of a restriction. I guess it is a big restriction classically for the Simpson reverse mathematics, but not. KL W-unique is like KL, but with the additional hypothesis, option 1. If R is a predicate such that if there are 2 infinite paths, then they're the same. And of course, you could also use option 2 to get a KL unique. And of course, these are related this way. And I haven't finished this yet, so. But I will observe that Bishop Constructivist has studied the results of strengthening the decidable Fan theorem by weakening the decidability requirement to a pi01 monotone condition of one kind or another. In fact, they are looking at a couple of particular conditions which give versions of the Fan theorem which relate very nicely with different theorems of constructive or not quite constructive analysis. Not quite constructive from Brouwer's point of view because he didn't accept the Fan theorem, but one of the things that the Bishop Constructivists focus on is which principles need to be added to Bishop's mathematics in order to get so-called non-constructive results. That is, results that they can't get within Bishop's mathematics. And so these versions of the Fan theorem are important in that sense. Very recently, Bob Lubarsky and Hannes Diener managed to separate two of these versions from each other and from the decidable Fan theorem using Kripke models, classical Kripke models. And in their paper, it's really interesting because they start out by saying, well, we tried this, we tried that, we tried realizability, we tried all these other things and nothing worked, so we came down to Kripke models. They were able to do it. Well, Koenig's lemma is a classical contrapositive of the Fan theorem, so it would be natural to consider the versions of Koenig's lemma for sigma 01 relations. And for example, Koenig's lemma for sigma 01 would be something like this. If for every y, there's an alpha and 2 to the n, such that for all x less than or equal to y, there is a z. Now this z is not, can be any integer, right? Such that sigma of alpha bar of x, remember that's a finite sequence of zeros and ones, and z is 0. Then there's an alpha and 2 to the n, such that for every x there's a z, such that sigma of alpha bar of x and z is 0. Constructively, of course, Koenig's lemma for sigma 01 entails Koenig's lemma with a double unique, sigma 01. And actually, Koenig's lemma double unique for sigma 01 entails weak Koenig's lemma, all of weak Koenig's lemma. And since m plus weak Koenig's lemma already fails to satisfy the Church-Kleene rule, I guess maybe I should stop here. But I do want to tell you what the Church-Kleene rule is. As an axiom schema, Church's thesis is too strong. As a rule, however, it is admissible in most constructive theories. So M has a decidable formula, which numeral-wise expresses y as a Gödel number of a computation of e of x, and a p functor representing, numeral-wise representing the result extracting function. Kleene proved that if T is FIM, or his basic theory B, or the small minimal theory M, then if T proves for every x there is a y, A of x and y, closed, then in fact there is a Gödel number E, we can find it, such that M proves for every x there is a unique y, T1 of EXY, in other words E is total, and T proves that squiggly E is a witness. If exists an alpha A of alpha is provable in T, then again, we can find Gödel number E, for which we can prove in the minimal theory that E represents, E is a Gödel number of a total recursive function, and T proves that squiggly E is a witness. In other words, what the Church-Kleene rule says is that we can only prove the effective existence of recursive functions. And this, Beeson observed long ago that this is really true for constructive theories. Essentially every constructive theory, there may be some exceptions, but essentially every constructive theory satisfies this rule. And it has become kind of a litmus test for constructivity. The interesting thing is that one can add to FIM, for example, Markov's principle, and this still holds. And in fact, one can add WKL to WNE, and it still holds. But if you go up to WKL, it doesn't hold anymore. So you need to stop somewhere if you want to stay within the realm of the vaguely constructive. Happy birthday.
These two definitions of uniqueness that you started with.
Yeah.
There's this range of sort of quasi-constructive principles, which Markov's principles are the most obvious. Do they become equivalent under some sort of small addition to constructive logic, or are they really sort of, you need to go almost all the way to classical logic to make them equivalent?
Well, okay, so I gave partly an answer to that for the WKL unique, where you need kind of half of Markov's principle, but not all of it. So your question would be under how much? That's a nice question. Okay, let me think about that. Okay, I'll get back to you if I figure it out. So.
A couple of questions about things you said about Bishop-style constructive mathematics. So the first is that you said Bridges had this version of at most one that it seemed a little peculiar. And why? What was his reason for choosing that version?
I think he tries to avoid anything that's negative. So.
But it starts with not equal.
No, apart. That not equal means apart.
Right.
Apartness is a positive notion.
You're right.
But he used not equal, actually. I was looking for the apartness sign, and I couldn't figure out how to do it in LaTeX. So I just used what he used, which was not equal. But then he explained that he meant by that apart. Okay? So apartness is positive, and the P prime is positive. Okay? Whereas not P is not.
Yes.
So I'm quite sure that that's
And
the reason.
P prime there, what was that again?
Let's see if I can get back there. Did I just go past it?
Yeah.
Yes. Okay, thank you. The P prime is some strong form of negation of P.
And what is that?
Well, if P is not Q, then P prime would be Q. Okay, but it could be something stronger than Q. For example, okay, let me go back to their option 3. Here, in fact, I suppose. I could have called this option 2 prime. But if instead of a decidable relation here, we had a more complicated one for our P, you see, then the P prime could be the classical dual, or it could be something stronger that is more complicated than just changing that not exists to an exists at the beginning, right? And he does, in fact, they do, in fact, I would have to give you chapter and verse, but they do, in fact, sometimes come up with, I think in each particular situation, one looks for a property which entails which is stronger than just the negation. In this case, it's simply, instead of taking not for all not, you take there is. So here it's really just 2 prime.
I think from a non-formal point of view, it's very classical. In looking at his actual book, it's taking 2 disjoint open sets that all have a boundary in common. It's either here or here. And being inside this open set is not necessarily being a negation. It can be much stronger than that.
Right.
So the tautological interpretation comes pretty close. I'm talking about the book itself.
Yeah, no, thank you. Yes, that helps.
The other, do we have time for that? So the other question is, you said that they're not too strong on formalizing or something like that, bishop people. But that you need that for independence results. What kinds of, I can imagine meta-mathematical independence results which say certain forms of the excluded middle are not provable. But are there interesting mathematical independence results that you have in mind?
Well, I'm not a mathematician, I'm a logician. So I'm just trying to provide the framework over which one could say that something does not constructively imply something else.
It's Rathjen and Lubarsky. In other words, they were looking at various forms of the axiom of choice and finding out whether they actually could construct Kripke models of which one is correct and the other isn't. So they were asking roughly you take 2 classically equivalent things and ask whether they're, when you give a particular constructive interpretation, they turn out to be quite different. And it turned out to be quite elaborate.
So I call those meta-mathematical.
You want something mathematical.
Does constructive mathematics do?
Okay, cool.
So, Joan, is there any version of a continuity rule like the Cluny Church rule?
Yeah, I've actually, I think that's a really interesting question. Yeah, I've tried to work with that. Yeah, I think that's a good idea. Yeah, I've called that a Browerian theory. That does satisfy such a result.
So may I also ask a small question? Classically, at least, once you prove uniqueness and existence of something, you can use the iota operator for definite article.
Yes.
What happens in the constructive framework?
We're talking, I suppose one could add an iota operator, but I'm not sure that it would really add to the understanding here. We're talking here about existence of unique operators under an assumption, right? So this is not an absolute existence. I don't know, for example, Planey would not want to add a name for this thing. But that's an interesting question. I don't know. I would have to leave that open. There are lots of open questions. Not many people work in this, so I would be happy if more people did.
Okay, so that's it. We can speak again.
I don't know how to close this. I'm afraid. Can we do that? Maybe Yanni. I think Yanni can.
We have the other
Oh, yeah.